Okay, well, welcome back everybody. And today, we're moving on with our study and look into bonding, and we're going to start looking at ionic bonding. Again, this is a type of bonding that you should be familiar with, but there's a few things we need to remember in terms of ionic bonding beyond what we've studied in Year 9 or Year 10 up until now. So we're now jumping back to topic 4.1 and starting where the IB textbook kicks off with our introduction. So, in topic 4.1, we're concentrating ionic bonding and structure. So much like with metals, we need to be able to relate the structure back to the type of bonding that we see. And these are the key understandings that we need to know. Okay, so we need to understand that positive ions, which we call cations, formed by atoms losing electrons. Okay, negative ions, which we call anions, formed by nonmetals gaining electrons. Okay, that the number of electrons lost or gained is determined by the electron configuration of the atom, and we can in particular relate this back to the subshell notation that we did in atomic structure. We also need to understand that the ionic bond is due to electrostatic attraction between oppositely charged ions, that under normal conditions they are usually solids with lattice structures, so crystalline solids. And then we need to be able to take that a little bit further, and we need to be able to deduce the formula and name of ionic compounds from being able to identify the component ions and polyatomic ions. So this is where it comes into we need to memorize some of those electrovalencies and ions that perhaps we've had on a valency table in the past. And then we need to be able to explain the physical properties of ionic compounds, such as volatility, electrical conductivity, and solubility, and relate them back to the structure, the same as we did with the physical properties of our metallic bonds. Okay, so we've seen this slide before when we talked about metals, but again, let's just reiterate the idea that this type of bonding between atoms determines the overall properties of the substance. Okay, so we need to be able to identify by looking at a formula what type of bonding we would see. So previously we talked about metallic bonding, where we would have metals only, so silver and gold or mercury or any of those other 80 plus elements that are metallic, they would have metallic bonding. Okay, but remembering again that all bonding is electrostatic, and in this case we're going to be talking about the attraction again between positive and negative particles, but in this case we're going to be talking about ions. Okay, so we're going to have our positive ions and our negative ions, where we're going to be seeing this cations attracted to anions coming together. Okay, so again, please remember that we're talking about an electrostatic attraction, so an attraction between oppositely charged particles, and in this case our particles are cations and anions. Okay, so again, another slide that you've already seen, but this is remembering that we need to be able to compare and contrast each type of these bondings. Okay, so we've already looked at metals with metallic bonding. Now we're looking at this metal and non-metal bonding here, which is ionic bonding. Okay, so we're starting to build up a picture of what type of elements will react with each other. Okay, so ionic bonding, anytime we see a metal with a non-metal, it's going to be an ionic bond. Okay, so if we think back to sodium chloride, which is an example of an ionic compound that we should all be familiar with, sodium is a metal. It's from group 1 on our periodic table, and then chlorine is from group 17. It's a halogen, so we know it's a non-metal. So if we can look at things and go, oh, that's a metal and that's a non-metal, then we can identify straight away that we should be dealing with something that would bond ionically. Okay, so ionic compounds. They are one of the most common compounds that we come across in our day-to-day life and every day in nature. Okay, we've talked about how metals can react and what they can form an oxide layer on their surface which stops them from being shiny. That oxide layer is actually an ionic compound. It's when the metal reacts with oxygen, so oxygen being a non-metal, and it forms an oxide which is an ionic substance. Okay, and when we look at that, it's kind of crusty and it's a solid, and it has different properties to the metal that was there previously. Okay, you're also familiar with ionic compounds in the form of most of our gemstones and things like that are different combinations of metals and non-metals that form crystal solids, ionic solids, and they are ionic compounds. The Melbourne Museum actually has a really good display on different gemstones and the ionic composition that they're made up from, including ones that glow in the dark. Okay, so again, because we see them naturally all the time, a bunch of observations were done, properties were tested, and a model was developed that explains how these compounds behave. Okay, also, they have then looked at those properties and found different uses for them. Okay, if you can think of like a couple of examples that you can keep in your mind about when you're dealing with ionic substances, it'll help you remember what the properties are. One I often remember is sodium chloride, table salt, that we put on our food, but here's some others for you. Okay, they can be used for their strength. So calcium phosphate gives strength to our bones, or calcium-based compounds such as limestone and sandstone in buildings. Okay, also calcium compounds form chitin, for those of you doing biology, which forms the exoskeleton in things like crabs and even some insects and things like that. So that calcium-rich skeletal structure is there for strength. They have high melting temperatures, so we use them in different ceramics to give them strength and heat resistance. Okay. They can conduct electricity when they're mixed with water. So we often see them in electrolytes, so Gatorade or hydrolyte that you might drink when you're feeling a bit dehydrated or when you've been sick with gastro. That actually is full of different salts, which are ionic compounds, which we need and help to increase your hydration. Okay, and then we also use them in batteries and different things like that. Okay, so we have huge numbers of examples of ionic compounds around us every day. Let's have a look at how they form. Hopefully you've seen these types of diagrams before. This is using our standard Bohr shell notation. Okay, so not our subshell, but our Bohr shell notation. Okay, where we just draw the shells and the electrons that are in them. Okay, so here we have sodium, and we're looking at, remember that sodium has 11 protons, so in a neutral atom we'll have 11 electrons. Sodium is a metal, so it will want to get rid of this electron in order to form a complete octet, to have this inner shell which is a complete octet, which makes it nice and stable. So it needs something like a non-metal to accept that electron. Okay, so metals have low electronegativity, so they lose their electrons easily. They want to get rid of them. Non-metals have a higher electronegativity and higher ionization energy, so they want to gain electrons. And remember that electrons don't leave an atom unless they have somewhere to go. Okay, so in this case, our electron is going to leave the sodium and it will actually jump into the empty space that's over here in the outer shell of the chlorine. When that happens, this chlorine becomes a chloride anion and the sodium becomes a sodium cation. Now they're oppositely charged, so they'll actually move closer together. So when we're drawing diagrams to show the electron transfer, we actually want to make sure that we show the arrow saying where the electron's going from and to, and then when we draw them again, you'll notice this one down here is actually closer together. It's showing the attraction, the electrostatic attraction that's pulling them together, indicating that the bond has formed. Our main thing for ionic bonding is remembering that every ionic bond forms as a result of transfer of electrons. Okay, there is an actual movement of electrons from one atom to the other atom. So the neutral metal becomes positive and the neutral non-metal will become negative because they're changing the number of electrons that they have. Okay, so when we define it, an ionic bond is the electrostatic attraction between oppositely charged ions. Okay, so that's our ionic bond. Think about the metallic bond and how we defined that. and what we said that was an attraction between. Okay, hopefully you remember that the metallic bond is an attraction between the positive cations and the negative electrons from the metal atoms themselves. But this time we're swapping electrons, so it's between the different ions that are oppositely charged. Okay, so this is another way of showing it, okay, that we have our sodium atom, our 281. Notice it's not in our subshell notation. Our subshell notation for this would be 1s2, 2s2, 2p6, so I'm up to 10, and then we have 3s1. And it's this 3s1 that is going to be lost, okay, giving us this stable configuration of the core electrons and forms our cation. Some of you may have different ways of remembering that a cation is positive. Some people use the fact that the term cat ion has a plus sign in it, okay, remembering that it's positive. The other one that you may have seen with some graphics is that cations are positive. So that relates back to your cats having paws. My bad drawing. Okay, but however you choose to remember it, that's up to you. You've just got to remember that cations are positive or positive, and then anions are negative. I tend to remember based on the anion because I remember anion starts with an, which reminds me of anti, and anti has negative sort of connotations in my mind, so I sort of remember the an, anti, anion. But however you choose to remember it, we've just got to remember that anions are negative, cations are positive, and they are the two types of ion that we deal with. Okay. So we're going to talk briefly about electronegativity. Again, we mentioned it a little bit already, but just getting this idea fixed in our head. Okay, so electronegativity is the electron attracting power of an atom. In the IB, we extend that to say it's the electron attracting power of an atom in a chemical bond. Okay, but basically what we're saying is that an atom's ability to draw electrons to itself. Okay, so a bonding pair of electrons to itself, which relates more to covalent bonding, but even when we think about this in terms of individual atoms. So atoms with high electronegativities will gain electrons easily. Okay, so they're going to form anions, which means all our non-metals, okay, are going to form anions because they have really high electronegativities, okay? And then atoms with lower electronegativity, so low ionization energy, which are our metals, they will form cations. Okay. Then another term for us to remember is electrovalency. Okay, you may have heard the term valency or charge. Okay, but what we're talking about when we do this is the electrovalency is the fancy chemistry term that we use to say the charge on an ion when that atom has lost or gained electrons. So the electrovalency of sodium, okay, so we've got sodium. When sodium loses its electron, it becomes plus, okay? So the electrovalency of sodium would be +1. Okay, if we looked at something like oxygen, okay, oxygen has 6 electrons in its valence shell. So in order to complete the octet, it's much easier for it to gain 2 than lose 6, and it's very electronegative. So it will gain 2 electrons, which will give it a negative charge, and we say its electrovalency then is -2. Okay, you'll notice every time I write this, even when I'm talking about a positive number, I include the sign. Okay, I don't leave it as assumed. Even when we're dealing with positive numbers, we often talk about 1, 2, 3, and we know that we're talking about positive unless we specify that it's negative. In chemistry, you need to specify the charge all the time. Okay, even if it's positive, we need to put that plus or minus sign when we're talking about electrovalencies. It's really important. Okay, so periodic table, which you always get in a test, okay, and in your data booklet you even have one which shows the electronegativity values in case you can't remember, okay, but the electronegativity values increase as we move from left to right across the periodic table. Okay, as we move across, you'll see that fluorine here has the highest electronegativity. So anything close to fluorine is going to have a high electronegativity. And if we look at this, it increases as we move from left to right, and it also increases as we move up a group. So fluorine is our most electronegative element, and if we look all the way over here in the diagonally opposite corner, we see francium here with 0.7, okay, so this is the least electronegative element, okay, so francium will be very metallic in character, fluorine's very non-metallic, and you'll notice here our noble gases aren't given an electronegativity value. They're very stable, so they don't tend to react easily. You will notice, however, xenon here. Xenon is the reason why we no longer call the noble gases inert. We used to call this the inert gases because they didn't react, and then a bunch of scientists discovered that xenon will actually react under very specific conditions. And so we had to change the terminology that we used and refer to these as the noble gases, which are highly unreactive, but they do react sometimes. Well, some of them do anyway. Okay, so if we look at this, our electronegativity, please remember fluorine is our most electronegative, then oxygen, nitrogen, chlorine. So all our halogens and those directly next to fluorine are very electronegative. So they will always form negative ions, okay? They're so electronegative, they just want to be able to grab hold of other electrons. They're not going to give them up very easily. Okay, and then our electronegativities decrease from there. Hydrogen, of course, is a little bit weird. Hydrogen can form positive or negative ions. The one we see most often is positive, but if we combine hydrogen with something like lithium, which has a much lower electronegativity than hydrogen, we'll get what we call hydrides, lithium hydride. And in this case, hydrogen will be -1 and lithium will be +1 because it's more electropositive. So in that case, we need to look at our electronegativity table and work out which one would win that electronegativity war. Okay, but this is in your data booklet. Okay, so you don't need to remember necessarily the values, but know if you can't remember the trend, just go to your data booklet to help you out. Okay. So when we look at what will form ions, okay, we get an ionic compound forming when a non-metal reacts with a metal, okay, and we notice when we look at this, particularly for the IB, we need to look at the electronegativity difference, which is another reason for you to become familiar with this table here, okay. So if we look at something like chlorine and sodium, chlorine has an electronegativity of 3, sodium 0.9, so let's put that here. Sodium has an electronegativity of 0.9, chlorine has an electronegativity of 3. Okay, if we look at this, the difference between these two, okay, if I take 3 and I subtract 0.9 from it, I'm going to get 2.1, okay? And our definition for an ionic bond forming is when the difference in electronegativity is greater than 1.8. Okay, so if it's greater than 1.8, we'll say it forms an ionic bond. Okay, and the greater that difference, the more ionic the character. Okay, so what we tend to see is anything between elements of group 1 to 3 react with elements of group 5 to 7, excluding carbon and silicon, because they don't tend to form ions easily at all. Okay, if we have an electronegativity difference of 2.1, it'll be an ionic bond. Okay, another point to remember, and we talked about this briefly, is that knowing the relative size of our ions. Okay, if you have a look here, this diagram here gives you the size of the atoms and the ion. Okay, so the red ones here are our cations, and what you can see, the grey area is your neutral atom. Okay, so this grey area here is the neutral atom radius, okay? And then this red one in here is the size of the ion. Okay, so if you see here, when we go from a neutral atom to a positive ion, it gets smaller, usually because we're losing that outer shell. Whereas if we go from a neutral atom of a non-metal, okay, the neutral atom again is shown in grey here, to the ionic radius, okay, you can see they get bigger. And this is because if you think about it, we're adding in another electron, maybe 2 or 3 electrons, into that outer shell, which already has electrons. And like charges repel, so when we put those electrons in, they're not held as tightly to the nucleus, and the whole atom just kind of swells up a little bit as they all repel out. Whereas with a cation, we're removing electrons, so the pull towards the nucleus actually gets stronger, so it sort of gets sucked in a little bit. Okay, so make a note of that, because we do need to know the relative sizes of our ions. Okay, so you need to know common ones. Okay, so sodium, which is a group 1 metal, will form +1. Okay, chlorine will go to chloride and form -1 ions. Okay, so when we look at these, we can look them in terms of our electrovalency. The neutral atoms have an electrovalency of 0. In the case of sodium, because we now have 1 less electron than we have protons, we can see that the difference will be +1. Again, specifying the plus, okay, making sure that we put it in rather than just assuming that someone knows that that one, you meant it to be positive. We've got to specify. Okay, and then with the chlorine, we have 17 protons and 17 electrons. When we form the ion, we still have 17 protons because that defines it as chlorine, but we've gained an extra electron, so now we've taken that extra negative charge, making it -1. Okay. When we have an electron configuration of a positive ion, okay, they lose electrons, but when they lose them, they form a filled outer shell, okay? They've lost all the electrons. This is now empty. Okay, so this outer shell is now empty, and this one is complete. Okay, so it has a complete octet, which makes it very stable, okay, and is generally why things are attempting to make ions, okay. In the case of negative ions, we go from a partially filled, so partially filled outer shell, okay, but you can see here, as with oxygen, it's got 6. In order to go back to a shell that is completely full, we'd have to lose 6 electrons, and that's just unlikely to happen. That's a lot of effort. So what happens instead is we gain 2 electrons. Those 2 electrons now come in and pair up with the 2 that we're missing, okay, which gives us our full octet of a stable anion, okay. So the higher electronegativity means that they will gain electrons. There's a cheats way, I guess it's not really a cheats way, but another way of using our periodic table to help us with this, okay, remembering that in our groups they all have the same valence shell configuration, okay, so group 1 will always form +1 ions, okay, whereas group 2 is going to form +2 ions, remembering that these are our metals, okay, so highly electropositive. As we increase, our electronegativity is increasing as we move across, then the ability for them to give them away is starting to diminish. But we see +3 cations occurring for group 13, so aluminium and boron, okay. Carbon and silicon, we say +4 or -4 because they can be either, but they don't form stable ions, okay. So there's only a couple of situations where we'll see those, and we don't often see them in terms of ionic bonding. We'll see that more when we do some more in organic chemistry, okay. But once we hit carbon and silicon, so we hit aluminium and boron, they're our +3s. Once we hit carbon and silicon, no, very unlikely for ionic bonds to form, okay, and then we start going into our negative ions, okay, which are -1, -2, and -3. Okay, and this has to do with the number of electrons required to complete that outer shell. Okay, so in this diagram, these ones in purple don't readily form ions. Okay, so they're more likely to form covalents, or in the case of noble gases, not form compounds at all. Okay, and then everything in white here, okay, all these have variable charges. So some of those we need to learn, or the name of it gives us an indication, and we'll talk about that later. But copper can form +1 or +2. Zinc is commonly +2, but can form others. Iron is +2, +3. So they have multiple different charge states. And I'll give you a periodic table which shows you the common ions when we're next in class. Okay. So we've already talked about this. Atoms form ions in order to form a more stable electron configuration. Okay, so we can show this by drawing out the electron configuration of the atom and then drawing out the electron configuration of the ion. Ions will always have an electron configuration the same as the closest noble gas. Okay. So sodium will lose one and form an electron configuration the same as argon, whereas chlorine will gain one and form an electron configuration the same as, chlorine will gain one and form an electron configuration the same as argon. Sodium goes to neon. Okay, so it depends as to which is the closest noble gas, and that will be the equivalent of the electron configuration that we see. So that's it for why and how we form ions, okay? So hopefully you have an understanding of positive ions are cations and are formed by atoms, in particular metals, losing electrons. Negative ions are anions and are formed by non-metals, gaining electrons. Okay, and that we can determine the electrovalency of those by looking at the electron configuration of the atom, either the Bohr notation or our subshell shell notation, and that remembering that the ionic bond is due to the electrostatic attraction, okay, again, must always have that, between oppositely charged ions, so our positive and negative ions being drawn together and forming attraction. And that's it. Okay. Until next time, see ya.